Our next speaker is Professor John T. Yates of the University of Pittsburgh, who got his Kendall Award in 1987. His talk then was short, Alkali Metal Activation of Chemisort Cobalt on Nickel 111. This time he's going to talk to us about imaging chemical bond directions in adsorbed species, a look at structural dynamics of surface species on single crystals. I'll give you the 5 minutes sign up here today.
I'll just hold it. Is this on? It's on? Yeah, it's on. Yeah. I messed up the I'll just hold it. That's okay. I can do this. Well, thank you very much, everybody, for coming to this session. I'm glad to be here myself. I wanted to tell you today about some work that we have been doing on the use of a technique to image bond directions for molecules on surfaces. So I wanted to begin with a general view graph showing some of the major issues that exist in surface chemistry and are important to the field. We certainly begin any area of surface chemistry, as Mike White has just shown us, as a matter of fact, with an understanding of the composition of the surface species. Then one goes in finer detail to the molecular structure and the site, the electronic structure of those species, the kinetic behavior of those species, and finally, in infinite detail these days, almost the dynamical behavior of simple species on surfaces. And so we have this flow of intellectual ideas from the fine grain, or from the coarse grain to the fine grain level. And then we have a flow of concepts or prediction of surface chemistry ideas that ranges from the field of dynamics and molecular structure and electronic character of species, which are interesting areas to scientists, to the field of surface kinetics and reactivity, which are also interesting and also very useful. And we've seen that in Mike's talk, for example, and before Summertide's talk, that this interconnection of concepts between these two areas is quite important. Now, in today's talk, I want to tell you about a technique that we've been using for a number of years called ESDIAD, which is electron-stimulated desorption angular distribution. And there are 3 things I want to leave with you regarding this method and the behavior of a particular system that we looked at. One has to do with the observation of the molecular structure of a species on a particular absorption site on a single crystal. We can see now in very fine detail how the molecules are bound and how they interact with each other on those sites. The interaction, sometimes through the intermolecular forces, causes a distinct tilting of the species on their chemisorption sites, and I'll show you some information about that. And in the last part of the talk, I want to show you some preliminary work that we've done where we think we've actually been able to image the active site for a catalytic reaction on a surface that was an interesting surface. The electron-stimulated desorption phenomenon has been known since the 1960s. Here you see CO molecules absorbed on a transition metal, an electron coming in, and various kinds of particles being ejected from the surface. Neutral CO particles, CO star, which in this case is an electronically excited CO molecule, and the ion fragments coming from the surface, the positive ion fragments. These are very easy to study, the ion fragments, the ones in the blue box, because you can count single ions very easily. And so in the 1960s, when electron-stimulated desorption was first being developed, it was the ions that people focused on because of the ease of measuring the ionic species. Now, as you'll see today, all the work I'll be showing you today is related to the angular distribution of CO star species, neutral species, which have certain properties that make them better for observation of surface structures than either of the ions shown there. The top view graph here, the top part of the view graph, shows the general schematic diagram that we all think about when a molecule on a surface or a bond at a surface is excited electronically. You see the CO bond represented in the bottom curve, and fast electronic contact excitation processes to upper repulsive curves, causing the liberation of an O+ ion in this particular case, which is ejected from the surface with kinetic energy, ranging generally from 0 electron volts or a little above, up to maybe 10 electron volts. So these ions come off with a great deal of kinetic energy. In 1974, I was very fortunate to work with Ted Matey and Yuri Tushevsky, 2 physicists, and we discovered that the ions that come off from oriented molecules come off in sharp beam directions, in certain directions relative to the crystal structure of the surface. And we devised an acronym, ESDIAD, to characterize that particular phenomenon, and also the technique is called S-dyad, electron-stimulated desorption, ion angular distribution. And here you see water molecules and CO molecules being excited by electrons and ejecting ions which come off in sharp beams from the surface. That information is now obtained in a modern apparatus involving digital acquisition, where a single crystal on the left is irradiated with an electron beam. A small spot on the crystal is excited. The ions, or in the case of the talk I'm doing today, the neutral CO star, the electronically excited CO star species, come off through a grid system into a set of microchannel plates, and then the pulse of electrons coming out the back of the microchannel plate hits a resistive anode device where it spreads radially from the point of impact to the four corners of the anode. And we measure the charge received in each pulse at the four corners. And the position computer here is able to calculate the x and y coordinates of arrival of that pulse of electrons, which is of course the same as the x and y coordinates of arrival of the ion, which tells you the trajectory of the ions coming from the surface. So if the CO molecules were in fact all inclined to the right on our surface and electrons came in, a beam of CO plus ions would come out to the right, as I've tried to schematically show in the top part of that diagram. So we use S-dyad in many different ways to look at the structure of species. This is a sort of a composite slide of the beauty of this technique for seeing symmetries on surfaces. This is a composite of many S-dyad measurements on different systems showing the lovely, this is actually raw data, all of it, showing the lovely distribution of ion patterns in space, which is related to the intimate molecular structure of the species on the surface in each of these cases. Now, what I'd like to do today is to talk about platinum 112, a stepped single crystal surface. Platinum 112 contains terraces of 111 orientation as shown here, separated by steps which have 100 orientation. So the terraces are a simple post-packed structure shown inside view here, and the step crystals contain the 111 terraces and 100 steps. And the coordination number for the platinum atoms in this step crystal are respectively 7, 9, and 10. So you might expect that these three different types of platinum atoms exposed on this crystal would have different chemical properties because, simplistically thinking, the coordination of those atoms to the bulk is different. So we want to examine the behavior of carbon monoxide as it comes in and samples this stepped and regular single crystal surface. Now on platinum, when carbon monoxide is absorbed and bombarded by electrons, three different kinds of particles are ejected from the surface. From the terminally bonded COs, CO plus is produced. These have a kinetic energy of about 1 volt. And unfortunately, as they escape from the surface, they are deflected toward the surface because of the interaction of the ion with its image in the solid, giving a polar angle that is larger than the true polar angle of escape. We know how to correct for that, but it's a deficiency in measuring ions that you do have these image potential effects to deal with. Fortunately, CO terminal, also on platinum, yields copious yields of a neutral particle, CO star, the A triplet pi metastable, which carries with it 6 volts of electronic energy, which is enough to excite the channel plates. So we can actually image the direction of emission of CO star, and CO star has a dipole, but the dipole image effect is small compared to the single charge image effect, and so its deflection from the direction of emission from the surface is very small. And finally, bridging CO between two platinum atoms produces O plus ions having a kinetic energy of about 6 volts. So by changing the retarding potentials in our apparatus, we can separate all three of these particles and measure the angular distribution of all three in this particular experiment. We would retard the 1 volt ions and see this species and this species. We would retard the 1 volt and the 6 volt ions, and only the neutral species would get through, and we could measure the angular distribution of those species. So the fact that there are 3 species coming on causes no trouble. Now on platinum 112, we're dealing with a surface where the macroscopic plane of the surface is inclined 19.5 degrees from the terrace planes, which are 111 in orientation. And when we adjust the temperature of the crystal to the correct temperature, a little above 100 degrees Kelvin, nature does a wonderful thing. It allows you to absorb molecules on this complex crystal, but they tend to migrate on the terraces as precursor species of chemisorption. And finally, they end up localizing themselves on the step sites. So this step on the surface, or these steps on the surface, are the final residing places for the molecules added to the crystal. The migration takes them there. So you have the possibility of actually loading up the crystal and lining up CO molecules next to each other on the steps in close formation, and watching the interaction between those species as they interact on the surface. So let's look and see what happens to the CO molecule as it crowds itself on this particular step plane. Under the conditions of the first picture here, we see the angular distribution of CO star, the neutral species, when the steps are 50% filled, so there's an empty space between every CO molecule. And we get primarily a single beam coming off the surface at an angle of minus 20 degrees to the macroscopic plane. That's almost 40 degrees down from the 111 planes that compose the terraces of the crystal. So the molecules are definitely leaning downstairs towards you on this crystal and are being excited. The metal carbon bond is being broken, and CO star is coming off along the direction of that metal carbon bond. 40 degrees down from the 111 planes and 20 degrees down from the macroscopic crystal plane. And as we raise the coverage of carbon monoxide above this level, we see an attenuation of this particular centrally located beam, shown here, and two auxiliary beams to the left and right, exactly parallel to the edges of the steps, are observed. So the molecules, as they fill up these steps, are tilting laterally from each other, making the green beams here. That's at 3/4 filling of the steps. As the steps are filled further, the green beams are extinguished, the red beam is almost completely gone, and one ends up with a pair of yellow beams, which in fact are CO molecules coming off downstairs and upstairs. So there are orthogonal tilt directions which depend upon the local coverage of the molecules on the step. And this particular pattern is only observing molecules on the step. It turns out that the terrace molecules, which are also fill in the backside of this pattern and are not shown here for the purposes of this talk. So we have evidence then that orthogonal tilt directions take place as the local crowding of molecules on these one-dimensional arrays of COs increases in the experiment. And so you've all thought now of what's happening, a very simple picture that we've evolved. When the step, looking at the step ends on here now, when the step is half filled with CO molecules, the molecules are independent of each other. There's a space between each one, and they're tilted down or out from the view graph toward me by 20 degrees, minus 20 degrees here. But as we fill in some of these empty spaces between these CO molecules, we get a lateral repulsion to the left and right as species which I call triplets are produced on the surface. And the molecule on the right can tilt to the right because there's an empty space next to it. And the molecule on the left can tilt to the left because there's an empty space next to it. And the molecule in the center is also being attenuated as 2/3 of the molecules are tilting over in this particular condition. As we continue to fill up the holes in this one-dimensional array of molecules on the surface, to relieve the strain that exists from the repulsion of these molecules, the molecules do the only thing they can do when they get crowded together, is to tilt backwards and forwards in the high coverage conditions where there are no empty sites left on the surface. So you get a 38-degree tilting in these staggered structures as you fill in those empty defect sites on the step surface. And finally, you can fill the steps up completely with the forward and backward filled with CO molecules. So we know the angle of tilt is about 13 degrees to the left and right. We know the vibrational frequency of the molecules, so we know something about the forces that hold the molecule there. And we can calculate from the dipole moment what the electrical forces would be laterally between these molecules. And it turns out that dipole-dipole repulsive forces between CO molecules on this step is only about 5% of the amount of energy needed to cause them to tilt. So what you're seeing here are not primarily electrical forces between dipoles. You're seeing the Pauli exclusion principle working, where the molecules are squeezed together and their interpenetration of the electron clouds causes them to repel each other and to tilt in certain directions, which is dependent upon the coverage on the surface. Well, now what I'd like to do in the last part is to tell you how we've used what I've shown you today already to study the details of the reaction of chemisorb carbon monoxide and oxygen on this step crystal to make CO2. Here's an S-dyed experiment at the top for oxygen chemisorb on a platinum 111 surface, shown inside the view here. And the O+ ions that come off when electrons hit the oxygen atoms come off in a direction which is normal to the crystal. We think that means that the oxygen is bound down in a deep three-hole site on the surface. When it's excited, the repulsions from those three bonds are balanced, and off comes the oxygen plus ions in a normal direction. But when we work on the step crystal, the normal to the terraces on the step crystal is given by that red line at 0, just as it is up here. The O plus ions on the step crystal preferentially bond to the step sites and give an O plus beam, maybe two of them, at high coverages, which is almost 40 degrees rotated downstairs from the normal to the terraces. So this is evidence that the original oxygen that we put on this surface seeks out the step site and bonds in such a way that it will push O plus ions off in the downstairs direction by an extreme amount of 40 degrees compared to what it would do on the terrace. So the oxygen goes to the step site initially on the surface. Now, if we load the surface up with a small amount of oxygen on the steps, and then at low temperatures, below the migration temperature of CO, we put carbon monoxide on this surface that already has the steps partially filled with oxygen. The carbon monoxide seen here is absorbing on the terraces and giving a CO star beam, which is perpendicular to the terraces. So the CO stays away from the steps. It binds on the terraces where it lands in most cases. If we warm it up from 90 Kelvin to 230 Kelvin, you can see that the CO molecules on the terraces, staying away from the oxygen atoms there, suddenly move to the steps and tilt over in the direction that we've already seen for the absorption of pure CO. So you can see the migration from one site, the terrace site, to the step site occurring here just by raising the energy above the migration energy on the surface. As this takes place, no carbon dioxide is produced. So there's no chemistry here. It's just a site change that's taking place on the surface. And now, if we add additional carbon monoxide to this particular surface, we fill in the green distribution here, which is related to COs, once again, coming in and it's orbiting on the terraces. So we can move the COs around from one site to the other in a controlled manner by knowing about the dosing and by having techniques that specifically detect the chemical sites that are present on the surface. So now the experiment we've done is to redo that, except to use isotopes of CO. Put the oxygen on first, as shown here, then to load up the step sites with one isotopic variety of CO, and then just at that point to change from CO16 to CO18, called CO dot, and to load up the terraces with CO dot. So now we have a surface that has the CO molecules on different sites at the temperature of absorption, and the oxygen, unfortunately I must say, we do not know exactly what happened to the oxygen. It still may be on the step, it may have migrated out, but it's there somewhere. Well, if you do that experiment with the isotopes, this is a side view, a little bit bigger picture of what we are dealing with. We label CO next to the oxygen somewhere on the surface, as shown here, and unlabeled CO on the step sites. And if we warm the surface up and look with a mass spectrometer at the production of CO2 from the interaction here, one finds that below 200 Kelvin, the first CO2 to be produced is exclusively CO2 being produced from the COs that were put on last that are definitely on the terrace sites on the surface. The experiment shows that the most rapid formation of CO2 at low temperatures in the first stages of CO2 production is coming from molecules not on the steps, but at least from a CO molecule that is present on the terrace. The active site in this particular regime of chemistry is the terrace site rather than the step site for this associative chemical reaction on the surface. Here's the actual data. We've done it both ways. We put the oxygen on, we add light CO, we displace that light CO, and then to the terrace we add heavy CO, and we simultaneously look with a mass spectrometer at mass 47 CO2, heavy CO2, and mass 44 CO2, light CO2, and we can see down here below 200 degrees Kelvin that it's only heavy CO2 that is produced initially in the first stages of the reaction. Okay. We now reverse the experiment, just to be sure, putting heavy CO on first, then light CO on the terrace, and tune with the mass spectrometer, and now mass 44 CO2, which is the light CO2, is produced exclusively below 200 degrees Kelvin. So it's a very clear effect where one type of CO is more reactive than the other on this model surface. How can we explain this? Well, we know from other studies that CO on the step is more strongly bound by about 7 kilocalories than CO on the terrace. So we should think of the step sites as being more stable thermodynamically than the terrace CO sites. It may very well be that this difference in binding energy of 7 kilocalories between the two kinds of CO, shown here and here, is in fact determining the height of the barrier to make CO2 due to its transition state here and here. So the 7 kilocalories difference in binding energy adds 7 kilocalories to an activation energy here compared to here in a simple model. That initial binding energy may be the thing that determines the propensity of one CO as compared to another to react on the surface. So what I tried to do is to show you, first of all, that digital S-diode is able to locate absorption sites on single crystal surfaces and to follow the migration of a molecule from one site to another under controlled conditions. We've seen evidence that under certain conditions of coverage, with 3/4 covering of the step, the tilting takes place in certain directions, and then when we fill in the sites on the surface, tilting also takes place in the orthogonal direction shown here. We've used controlled absorption methods with the isotopic CO to load up this step surface with CO molecules on one place or another. And we've seen a particular propensity for the Paris CO to be more reactive than the step CO in the CO2 reaction. I'd like to end with, almost end with an acknowledgement of the two people who've done this work, Andres Salvo, a very talented physicist and chemist from the Hungarian Academy of Sciences, and Mike Henderson, a postdoc from Mike White's lab, who's just been doing a fantastic job with us at the University of Pittsburgh. The support for this work comes from two places. The tilting CO work has been supported by the Air Force, and the CO plus oxygen work has been supported by the Department of Energy, Basic Energy Sciences. And I'd like to finish with one final graph. It's a picture of, I don't know whether they're chemists or physicists, I think they're physicists sitting, derelict physicists sitting on the steps here, and it says quarks, neutrons, mesons, all those damn particles. You can't see them. What they've done is to drive me to drink, and now I can see them. And I think that's relevant to this talk. So thank you very much. Are there any questions? I might as well ask the question.
Have you looked at the same reaction on a flat surface to determine
No, I definitely
Yeah, the flat surface has entirely different kinds of absorption kinetics. More like the you see at high temperature. That low temperature is not working.
So the step is
Yeah, the step is really dominant just in terms of absorption.
Pure symmetry would be faster, but also on the trajectory of the original.
Well, okay, there are actually a few experiments which indicate that this phenomenon of S-diode is almost completely independent of electron angle because you're dealing with excited species. And the excitation probability may differ slightly, but only by 10 or 20%.
Is there theoretical confirmation of that?
Yeah, basically the way to think about it is if the thing suddenly becomes very repulsive, it certainly samples the whole set of sites around it, but it's most strongly influenced by the closest absorption site underneath. And so the repulsive energy is focused along that bond. But there is the final state effect of the charged particle being tilted toward the surface, which we must take into account in order to make an analysis of the situation.
Well, thank you very much for this talk.